All right, so I just want to go over all the things you're supposed to be doing right now, and then we're going to finish an example and then start chapter 5. Okay, there is homework. There's homework, I think 3.5, 3.6, 4.1, 4.2, 4.3. And I think we stopped there. Soon I'm going to make homework for 4.4 and 4.9. But homework. I do want to list it out. I just want you to know like exactly what needs to get done. So these sections are 3.5, 3.6. Then 4.1, 4.2, 4.3. It's due on Monday, May 2nd. Okay, and today we're doing notes. Tomorrow I'd like to do a quiz. You can take like the first part of class as much time as you need to work on a problem where you find intervals of increasing, decreasing, concave up, concave down. And if you miss class that day, I'll post the quiz to Canvas. You can either turn it in online or just hand it in to me later. I'm also going to pick some questions where you need to use L'Hopital's rule. Okay, cool. We're going to finish 4.9. I'm going to put some information from the example up, but then we want to get to part B. So, for example, there's a person who throws a rock. Off of a cliff that's 350 feet tall. All right, we have an initial velocity of 10 feet per second. And we already found the position function for part A. It was S of t equal to negative 16t squared plus 10t plus 350. Let me see. Okay, the next part is to find the time t when the rock hits the ground. And I think a picture is going to help, and we'll kind of keep that picture over on the side. When does the rock hit the ground? Okay. We started a sketch yesterday. I had this as values of t, and at t equal to 0, that's where your person is standing at the top of the cliff. Throw a rock, and it's going to hit the ground. So we want to find this spot right. Okay, so we've gone from a height or position of 350 to a position of 0. So we're going to have S of t equal to 0 and solve for t. Okay, by setting this S of t, the position function, equal to 0. Okay, 0 equal to negative 16t squared plus 10t plus 350. Okay, use the quadratic equation to get two solutions or two values of t. I don't really think we need the picture anymore. I want to point out that something that comes up with problems like this, like say you're in a physics class, as part of the question could be, when is the rock at its highest point? I just want to point out that would be right there where the tangent line is horizontal. So that's when f prime of x, when the slope of the tangent line is 0, when f prime of x or f prime of t, whatever number t is equal to 0. But we don't have to even worry about that with this problem, but just pointing out, you get to that highest point when that tangent line is horizontal. And you've got some value of t where the derivative or the slope of the tangent line would be 0. Okay, that's just on the side, if you were asked that question. But we want to know what t looks like here. That's where you're at your lowest position, the ground. Okay, you have -10 plus or minus the square root of 10 squared minus, let me make sure, minus 4 times -16 times 350. Over 2 times -16. Okay. So the first number I got was -4.375. Okay. Or t could be 5. We don't use any negative values when we measure time. So we're not going to use this -4.375, and we're going to have t equal to 5 seconds. Okay. Last part. I think it was, what is the impact velocity when the rock hits the ground? Yeah, I mean, you can just say, what is the impact velocity? So impact means you've hit. Okay, so like right here, when t equals 5, we'll find the velocity with that function v of t. Okay. Okay, we did that yesterday, somewhere in our scratch work for part A. V of t was well, we can put v of 5. would be, let's see, negative 32 times 5 plus 10. I got negative 150 feet per second. We made it to chapter 5. And I just want to let you know that from now on, we'll be working with antiderivatives. And let's see, anything else? I guess the only thing I can think of is instead of making a homework assignment for different sections of chapter 5, I'm going to make one chapter 5 homework. It'll be due at the end of the semester. Okay, 5. Chapter 5 is about integrals. Okay, 5.1 is finding an area under a curve. Okay, let's talk about this area. It's an area A. Okay. Under a, well, we'll put this in the next part. Under a function, y equals f of x. Okay. And you want to go from x equals a over to x equals b, because you'll be on an interval from a to b. Let's see, from x equals a over to b. You okay? No? Okay. Okay. All right, the area is bounded by the graph of f. Where f is continuous and positive on the interval from a to b. Cool. And okay, so between F and the lines x equals A and x equals B and the x-axis. Okay. Let's sketch this area. So our function f is positive and continuous. Okay, and we're going to look at the interval from A to B. X equals A over to x equals B. So the area is bounded by the graph of f. So this graph right here, this sketch of all the points x, f of x. And the x-axis here to here. And the vertical line's x equals A, so straight through here. This line, x equals B. Y is any number, x is always B. Okay, from that line to that line, the x-axis to the function. That's the area. Okay, we are going to start with finding an approximation of the area, and I'll talk you through some steps for that. And later, we'll figure out how to actually find the area using limits. Okay. Okay, so first, we're going to take that interval from A to B and split it up into n intervals of equal length. So you're going to partition your interval into subintervals. Okay, let's see. If we want to split that length between A and B into little strips of equal length, what we'll do is find this length. So what you want to do is find the length from 0 to B and then remove this part, the length from 0 to a. So what you're doing is taking b minus a. That gives you, like, take this value b, remove this value a. That gives you this leftover part. Okay. And then if you want n subintervals, then divide by n. So split this up into strips, all the same width. And we're going to call that little, it's called like a change in x, it's delta x. So this is delta x. So every subinterval has width delta x. Delta x is b minus a over n. Okay, then number 2, we're going to make some rectangles. So we build n rectangles. Okay, the rectangles have a width delta x. Okay, and for the height, there's 3 popular what's it called? Points to find heights at. But you can find the height, we'll talk about it in a bit. You can use the function evaluated at any point really, but the right end, the left end, and the midpoint is like the most popular. Okay, so you've got your width delta x, and we often use values of f at right endpoints, left endpoints, or midpoints for the height. Okay, so again, we're always going to use delta x for the width. And then depending on really what the question asks, you want to go to the right endpoint of your subintervals, the left endpoints of your subintervals, or the midpoints of your subintervals. And then from that point, find the value of your function, like evaluate x, send it through f of x, send it through f, get the output, that's your height. Sorry, I have a, I guess, very bored cat who's trying to get my attention. Chill. Okay. Anything else? Yes, then after you make all of these rectangles, add their areas together. So get the width times the height for every single one, sum all of those areas. I think I want to talk about notation and then just hopefully start an example, and that'll help with all of this, going through all of these steps. Okay, the only thing I'm kind of concerned about is like, don't be too scared of this symbol that's a star. The star is just, or asterisk, is there to tell you like you're really, unless you, the star means you can change from being either right endpoints, left endpoints, or midpoints. But if you're just doing right endpoints, you don't need to put the star there. The star is just to tell you it could be one of these three, or it could be any number, which we'll get to. Okay, here's the notation. Your area is approximately the sum. I'm going to go from I equal to 1 up to n of f of x of I, and we're going to put a star. So again, right now I'm using a star to say these x of i's could be midpoints or right endpoints or left endpoints. If you're like starting your problem and you know you're using right endpoints, you don't need to put the star here. You're just using your endpoints, x of I. But then send them through the function f, multiply it with delta x, and then add it to the next one. Okay, so the summation notation is just to add these values where you put your subscripts in, I equal to 1, then add the next one where I is equal to 2, all the way up till you get to adding the last one where I is equal to n. So f of x1 star times delta x plus f of x2 star times delta x plus. Keep adding till you get to the end and you add. F of x sub n star times delta x. Okay. We've already talked about delta x. Delta x is the width of the rectangle. It's e minus a over n. Okay. X sub I star is some number in the ith subinterval. It's going to be either a number at the far right end or left end or middle or whatever. So X sub I star is some X value. In the subinterval. It goes from X sub I minus 1 over to X sub I. So you got this little subinterval. You're going to pick one of the ends maybe, or the midpoint, or whatever point you want in this interval. Once you pick a number in that interval, put it through your function and get that output, get f evaluated at X sub I star. And then that's going to be your height of your rectangle. Let's see. I think a sketch will help. So we're going to draw another positive continuous function f. Make it a little bit more steep. Okay, and we're going from A to B. Okay, let's say n is 4. So we're going to create 4 rectangles. So let's first divide this interval in, we're going to in half. Then each of those will split in half. So right here, we're at A, and then this is A plus delta x, this is A plus 2 delta x, A plus 3 delta x, A plus 4 delta x. Each of these is a width of delta x. Okay, let's say we use, let's go with left, let's see, I use left endpoints. So for the first interval from A to A plus delta x, go to the left and pick A, send A through the function and find f of A, right here. And that's the height of the rectangle. So we're going to go straight over. we'll find its area. So next to subinterval, we were using the left endpoint. So we're going to go right here and find f evaluated at that point, right there. And that's the height of the next rectangle. Next interval, go on the left end, find f of that x value right here, and create a rectangle with that height. And last interval, go over to that left end of the subinterval, find f of that value, which would be somewhere here. And that's the height of the rectangle. This straight across. And then we're going to find the area. And we'll add all 4 areas together, all the areas of the rectangles. And that's approximately the area under the curve. We're missing these spots right here where we're, I guess where it's like empty, where we haven't considered that little piece of area. So whatever area we get is a little bit less than the actual area under the curve. Okay, we like to call A x naught, and we call B x sub n. Then the n subintervals look like this. The first one starts at A or x naught and goes over to x1. Then the next interval goes from x1 to x2. The next interval is between x2 and x3. Keep going intervals until you get to the last interval, which should be x of n minus 1 over to x of n, or over to b. So just to let you know, like I remember when I was first learning this, what was tricky to get used to was the indexing, this subscript, and also the summation notation. But I feel after a little bit of practice, it will be more comfortable. It was for me. Okay, I want to maybe just start an example. We only have a couple minutes. So instead, I just want to make a little like zoomed in sketch of this part and how we're creating these intervals and talk about endpoints, and then we'll be done. Okay, let's divide this into rectangles of equal width. Subintervals of equal width.
Kathy?
Yeah.
The camera's a little bit too low quality to see the subscripts
Okay.
of the intervals.
Yeah. Let
So
me try to write it out bigger, and then I guess that'll be it for today. Let me try that. Thanks for letting me know. Okay, I'm gonna relist these, but we're gonna go down this way. The first interval, it goes from x0 over to x1. Then x1 to x2. x2 to x3. Until you get to x of n minus 1 over to x of n. Okay, we'll kind of go through this again on Wednesday. And again, I want to like point out where your right endpoints are, and like maybe what your left endpoints look like. Also how to find midpoints, and then we'll go through examples. Okay, thank you.
Last thing, Cassie.
Yeah.
Last thing, Cassie. So can you write down like the topic numbers for the quiz tomorrow, please?
Yes, I will.
Like, specifically. That'll be very helpful.
Okay, I'm going to give you a function, and like the first part of the question will be to find intervals where the function increases and decreases, or if your function has a max or min. Okay, there's going to be a second part where you need to find if the function has an inflection point and where it's concave up or concave down. Okay, and then there's probably going to be one or two more, and you need to find a limit, and you're going to need to use L'Hopital's rule. So number 2 is probably like
Well, I was talking about like numbers, you know, like 4 point something, you know. Can
okay.
I write that down or not?
Yeah, no, I know I can find it. This one should be 4.4. The other one, let me see. Okay, this one is 4.3, both parts. Okay, any other questions?
That's it.
That's it. Oh yeah, and that's the end of that's
All
it.
right. Have a nice.
Okay, yeah.
And that's all that's gonna be in the quiz, right?
Yeah, that's all it's gonna be there. Those 2 topics or those 2 sections.
All right.
Cool. All right, thanks everybody.
Okay. Have a nice day, Cassie.
You too. Have a good day.